This is section 11.5, part 2. We're now going to take a look at vector-valued functions in 3-space. We've been looking at 2-dimensional graphs of vector-valued functions, so these are going to be some 3-dimensional ones. First of all, R of t is here, notice, a 3-component or 3-dimensional vector-valued function. So just like before, if I want to evaluate it at, say, the point t equal 3, all I need to do is plug 3 in for the t, and we'll be all set. So here I'm going to get 12, 9, 25. Technically speaking, this says that at time 3 seconds, we have a vector pointing to 12, 9, 25. All right, to graph vector-valued functions in 2-space, the 2-dimensional plane wasn't too bad. Graphing vector-valued functions in 3-space is going to take a bit more work, just like all 3-dimensional graphing does. But just like we got some kind of a curve in 2-space, we're now going to get some kind of a curve in 3-space. So the graph of a vector-valued function is going to be a 3-space curve. In general, as it says, it's really very complicated to draw these graphs, but there's just going to be a few special cases that we'll be able to look at doing by hand. I'm going to actually make us a separate Maple video for this unit. That's going to actually show you how to graph these things in Maple as well, because most of the time, unless they're these special cases, we'll need technology to help us draw these. All right, the first special case, one of the function components is constant. If that happens, we can usually draw the curve ourselves. What we do is we look at the other two components, the non-constant ones. Think about what that graph would look like. That's just a 2-dimensional graph, which we either know or we could use a calculator to help us figure out. And then we'll just move that to the plane designated by the constant component. So here's what I mean. Here's a 3-dimensional vector-valued function, but notice that the z value here is constant. What that means is that this curve, whatever it is, and we'll talk about that, exists entirely within the plane, z equals 5. So our curve lies in the plane z equals 5. All right, I'm going to start by drawing that plane. And then once I've analyzed my curve, I can just go ahead and add the curve within that plane. So z equals 5, 1, 2, 3, 4, 5 is right here. And this is just going to be a plane parallel to the xy plane. So horizontal, up here at a height, z equals 5. And remember, to make your graphs look good, if you sort of draw your lines parallel to the axes, it helps the reader see what you're trying to say. All right, what about the x and y components? Well, this says x equals 2 cosine t and y equals 2 sine t. We were just talking about those, right? When you parameterize with sines and cosines, you're looking at circles and ellipses. In this case, it would be a circle, since I've got 2, the same multiplier on both of them. In fact, that circle would have a radius 2. And since x is the cosine and y is the sine, we're going to go around this counterclockwise. So essentially, I'm just going to draw what we've just described up in this plane, z equals 5. I'm going to go 2 to the right, 2 to the left to establish my radius. It's easier to establish the radius along the y-axis because that's within the plane of the paper. It's more difficult to do it along the z-axis, or excuse me, the x-axis, since technically that's just the perspective, right? It's actually coming straight out at us. So I'm just going to kind of sketch in my circle from there. It won't really look like a perfect circle because it's sort of the perspective again. And then I'm just going to show with my arrows that I want to go around counterclockwise. All right, let's try another problem or two similar to that. In part B, this time it's the j component, or the y, that's constant. So the fact that y equals 4 here says that our curve lies in the plane y equals 4. So once again, I'm just going to start by sketching that plane. 1, 2, 3, 4 for y. And there's my plane, y equals 4. In fact, I didn't do it on the last one, but I could even label, oops, y equals 4. I didn't do it on the last one, but I can even label the plane to make it more obvious to my reader. This was the plane z equals 5, right? This is the plane y equals 4. All right, what's going on in that plane? Well, the curve this time is determined by the x and the z components. X equals 3 sine t, and z equals 3 cosine t. Once again, we've just been talking about these. It's a circle of radius 3 this time. And since x is the sine this time rather than the cosine, this one we're going to go around clockwise. So, coming out here, this is the center of my circle. Here on the y-axis, I'm going to say radius 3 means I'm going to go up 3 in the z direction and also down 3 in the z direction. That establishes radius. Again, because of the perspective, it's more difficult to do that in the x-axis, so I'm just going to kind of sketch my circle. Because, again, it's slanted, it has more of an oval look to it, but it really is a circle. And this time we want to go around clockwise. Like so. All right, let's do one more. This time it's the x that's constant. So my entire graph, my curve lies in the plane. X equals 3. So we are 3 on the x-axis. And I'm just looking at a plane that's parallel to the YZ plane. And again, just to help my reader out, I could even label that x equals 3. All right, what does the curve itself look like? Well, y is equal to t, and z is equal to t squared. If I put that back together, if I substitute y in for t, I could say that's really just z equals y squared, which is simply a parabola in the YZ plane. So I'm going to take that parabola in the YZ plane, and I'm going to move it out into the plane x equals 3. So instead of the vertex being at the origin, the vertex is now here on the or the x-axis. And I'm just going to kind of sketch in a standard parabola. Again, it doesn't have to be perfect. We're looking for a general idea. If I want something more accurate, I'm going to use a graphing device of technology. So that's the first situation that's usually graphable by hand, something where one of the variables is constant. By the way, I should also mention, if you just happen to get parametric equations for the curve that you don't recognize, remember that you can always use your calculator for those. Let's just pretend for a moment that I didn't recognize that as a parabola. If you go to your calculator and put it into parametric mode, right there. It's usually in function mode, but I'm putting it in parametric mode now. Then I can actually put in my parametric form, right? In this case, it's going to have to be x and y, but I know for me it'll be y and z. So I'll put t in for the first component and t squared for the second. And let's see where my window's at. -5 to 5 for the t's is fine. T-step is usually generic. Around 0.1 is good. Everything looks fine. And there we go, and it graphs the parabola for me. I now know the shape that I then took and drew in the plane x equals 3. So if you happen to get something you don't recognize, by all means, feel free to use the parametric mode on your calculator to draw the initial graph. All right, there's one other case that I claim we can usually kind of figure out by hand what the graph looks like. And that's the case where one of the components is linear. In that case, once again, we'll look at the other two variables, figure out what that graph would look like, and then as far as the linear piece, we're going to essentially take our graph and stretch it in the direction indicated by the linear component. This will probably be a little bit more clear when we do a couple of examples. So this first one, r is 4 cosine t, 4 sine t, t. Notice the linear component is the z. Okay. I'm going to come back and talk more about that in a couple of minutes, but let's think about the other two components first. X equals 4 cosine t, and y equals 4 sine t. Circle of radius 4. And cosine is our x, so we are going counterclockwise. Now, we know what happens there, just a circle. We're imagining going around and around the circle. But notice that z doesn't stay the same as we go around this circle. Instead, as we go around the circle, z gets bigger and bigger, right? The further around the circle, the larger the z value. So instead of just sitting down here in the xy plane and going around and around our circle, as we go around, we're also going to have to move up the z-axis. And we're going to essentially get sort of a spiral, or more formally, a helix out of this shape. So the fact that the z has a positive slope means we're going to stretch upward. Let's give this a try. I always like to have some kind of a starting point. So let's start at t equals 0. Unless I'm given a specific range of values for t, I'll typically start at 0. Of course, we could go backwards from there as well, but I'm just going to start at 0 and go forwards. So r of 0 is 4 cosine 0, 4 sine 0, 0, or 4, 0, 0. Meaning I'm going to start on the x-axis out here at 4. Now I'm going to go around in a radius of 4. Let me just mark the 4s. And as I go around, I'm also going to go up the z-axis. One last thing. I want to go all the way around one time by the time I get to t equal to 2 pi. So when z is 2 pi, 6.28, about here, I should be one full circle around. Let's see if we can do that. We'll start here. I'm going to go up and around. And by the time I get back to directly above where I started, if you kind of imagine the slant of the x-axis, I'm up at 2 pi. That was one full time around, so that was from 0 to 2 pi. This is t equals 0, this is t equal to 2 pi. Now, of course, I could continue. I could go beyond 2 pi, and I would simply continue to make these circles while I stretch upward further and further. You can imagine almost like a slinky that's being stretched, if you will. Right above here would be t equal to 4 pi. Every time I go all the way around once, I go up another 2 pi on the z-axis. All right, so again, we end up with this shape, which is a helix. Let's try another one kind of similar to this. In part B, the linear term this time is the x. And we'll come back to that in a few minutes, but let's think about the y and the z first. We've got y is equal to 3 cosine t, and z is equal to 5 sine t. So with different coefficients, this is an ellipse. And y is cosine, that's the first variable, z is sine, so we are going counterclockwise. All right. So we've got an ellipse if it were in the yz plane, but it's going to get stretched in the x direction. X-axis is forward and backward, right? Because the slope is negative, we're going to stretch this backward, or in the negative x direction. So let's get a starting point again. Again, unless I have a reason to do otherwise, I'll typically start at t equal to 0. And r of 0 would be 2 minus 0I plus 3 cosine 0j plus 5 sine 0k, or 2I plus 3j plus 0k. So I'm starting in the xy plane at the point 2, 3. Right about there. That's our t equal to 0. Now I'm going to go around this ellipse. Here's my y equal to 3 already in the y direction. And I'm going to go around this ellipse. I'm going to go all the way up to z equal 5. 1, 2, 3, 4, 5. 3, 1, 2, negative 3, 1, 2, 3, 4, negative 5. So I'm essentially going to follow around that ellipse. But as I go around the ellipse, I also want to go backward in the negative x direction. So I'm going to spiral around and back, like so. More difficult to draw, I think, than the upward one, but you get the idea. All right, let's do one that's not a helix. I'll wrap up this part. In C, I've got t, t, and t squared. Now there are actually 2 linear terms this time. Both the x and the y are linear, so I just kind of have to pick one. Since we've already looked at one where we considered z the linear term and one where we considered x the linear term, I'm going to consider y the linear term this time, although I could have done it either way. So let's think of y as being linear. right? Y is right and left. Since it's got a positive slope, that's going to tell me to stretch in the positive y direction, or to the right. All right, what about the x and the z? X equals t, and z equals t squared. So in fact, since t is just x, that's just like saying z equals x squared. And we have a parabola. I'm going to get a starting point again. At t equals 0, we would have r of 0. And notice it's just going to be 0, 0, 0. So I'll start here at the origin. That's our t equals 0 position. And then I want to draw a parabola, z equals x squared. Notice that would be this parabola in the xz plane. But since I'm only going to go for right now, at least for positive values of z, I'm going to be looking, positive values of t. I'll be looking only at the positive values of x, and they'll have to be stretched right or forward in that y direction. So instead of staying in the xz plane, this is going to come forward as I go up. Kind of like so. And if I allowed for the negative values of t, they would have gone backwards in the negative direction. But I'm only going to draw the ones that are coming forward, the positive ones. All right, as you can see, it can be very challenging to draw these, to get the perspective right, and the ones that we've looked at so far have actually been pretty simple ones. Generally speaking, even these can of course be drawn better using graphing technology, and if they get any more complicated than this, we really need our graphing technology to help us out. So I'm going to actually do a separate Maple video to just kind of introduce you to drawing these things on Maple. We'll relook at a couple of the ones we already did, and then we'll graph some of the more complicated ones which are also illustrated here in your course pack for you.